Okay, so for the last time, here we go. Is that sad? You guys sad that classes are over?
Yes.
No, really, actually.
I stayed to you for like 3 more minutes.
There were more classes that you take. Anybody graduating?
Sorry, everyone else excited?
So what we're going to do today is simply go through your study guide. This is available on Canvas for you. Go to the module section, all the way down at the end. Final exam study guide. This will be very similar to your midterm study guide because your final will be very similar to your midterm. Same format, 3 sections, kind of a short answer, fill in the blank for the first section, an analysis. You have to kind of interpret some code or give a little bit more of an in-depth response compared to the first section. And then the third section of your test is a free response, where you're working out larger problems. There's not as much hand coding in the final as there was on the midterm. For the midterm, your free response section, you did a good bit of coding. You filled in some partially written methods to a class. Not so much on this one. To be doing something a little bit different. Okay. What we have listed here is all of the concepts and the topics that you will find on your final. As we said with the midterm, if it's on the study guide, it's on the final. If it's not on the study guide, it's not on the final. Okay, I want to be transparent about the content of the test so that you guys know what to study and how to prepare. Questions before we get started? All right, we're going to go through this very quickly. Again, all of this is a review, and about all of these sections, I could say the same thing. So everything that's on your final, well, everything that's on your study guide is mirrored on your final. And all of that comes directly from what we talked about in class. Okay? So if you want a little bit more information, you want to go back and review in a little bit more depth than what we're going to cover here, simply go back to the topic outline, go back to the programs that we wrote for that topic. You can go back and watch the videos for it as well. Okay? Everything that we talked about here, we have previously talked about in class at some point. Okay? There shouldn't be anything strikingly new. All right, so as we go through here, I'm going to kind of cover it briefly. Now's your opportunity to ask any questions, ask me to clarify anything, or go in a little bit more depth if something's not clear to you. Okay? All right, so number 1, algorithm complexity analysis. Okay, you need to be able to explain what the dominant term is. Okay, so the dominant term, if we have an algorithm or a function that's expressed in that notation, functional notation, where we have like f of x equals 18x squared plus whatever. That's functional notation. Okay? If we have an algorithm in functional notation, then we can pick out the dominant term. And the dominant term is simply the term that contributes most to the growth of that algorithm. Okay? When we're identifying the dominant term, we ignore constants. So if we have something that's we have an algorithm expressed in functional notation, a of n equals 34 n squared plus 90 n cubed plus n plus 4. We have this algorithm A expressed in functional notation, and we're going to identify what the dominant term is. First of all, the dominant term is the term that contributes most to the growth. And because we ignore constants, the only thing we're going to consider are the 3 terms. Okay? We ignore 34 because it's a constant, 90 is a constant, and so is 4. So clearly, I said n cubed, but I wrote it 2. It should be a 3. That's a 2. N cubed contributes more to the growth than n squared does. Okay, does this make sense? Everybody good? both with what the dominant term is and also how to pick it out. All right, part B. You need to be able to express an algorithm's complexity in big O notation. This is really simple. You take the dominant term that you picked out, like we just did, and you put it inside of parentheses next to a big O. Okay, so in the example that we just covered, we identified the dominant term as n cubed, so we would say this is an O n cubed algorithm. Right? Just like that. Good? Questions? Here we go. Know the complexity of the add, remove, and lookup or search operations of every data structure we discussed in class. It seems like a lot, but it's really not. Okay, so let's run through these really quick. And again, we've covered these before. This shouldn't be new. I will also say that for some of the structures we didn't emphasize certain operations. Like for stacks and cubes, we didn't really emphasize what it costs to search them because you shouldn't. Okay, but still good to know what the cost is. So let's start with stacks and queues. It's the same for stacks and queues, so we'll kind of clump them together. The cost to add to a stack or queue is what? 0.1. Good. Cost to add to a stack or queue is 0.1. Cost to remove from a stack or a queue is 0.1 as well. You should not search it, but if you did search a stack or a queue, it would be O n. Right. 0.1 add, 0.1 remove, O n search for stacks or queues. Questions on that? Okay. Next one. Heaps. Cost to add to a heap is O. No. Log n. Very good. Cost to add to a heap is O log n. And remember, when we're talking about that, the n is the number of elements in the data structure at the time that we go to add a new one. Okay, log base 2 of n, log n. Cost to remove from a heap is just good confidence. Log n. This is why we review. Log n. Cost to search a heap, you shouldn't, but if you did, you would get O n. Very good. Someone's going to pass it. All right, so review. Heaps. Add is log n. Remove is log n. Search is n. Questions on those? Okay. After heaps, we talked about binary search trees. Cost to add to a binary search tree is log n. Remove
Log in.
Log in.
Correct. We didn't talk much about removing. I won't ask you about that on the test. Searching.
N.
Close. Binary search trees are really good at log in. Log in. And the last one that we talked about, the hash table or a dictionary. They will be called hash tables. All right. Add, remove, and search are all
Log in.
good guess. No, 0.1. Add, remove, and search are all 0.1s.
And that's for the hash table, right?
Correct. That's it. Question?
What was that for again?
Hash tables. Moving on. Recursive algorithm analysis. This is the fun part. You guys remember this?
Yay.
Be able to explain what recurrences and initial conditions are. Okay, be able to explain. Now, when I say explain, I don't mean simply regurgitate a definition that you don't understand. I'm interested in you describing it in your own words. Now, if you use some of the same words that I used in class, it's okay. But understand that I'm not looking for some specific definition. How you convey this is up to you. Okay? So, a recurrence is simply an expression of a function in terms of itself at another point. Okay, so we are defining a function in terms of itself at another point. Okay, and that other point is a subsequent recursive call. Okay, we're defining a function in using itself as the basis, like or giving the definition of a word using the word. But at another point. That's the definition of a recurrence. An initial condition gives us, okay, so again, it's an expression of a function. But whereas a recurrence was an expression of a function in terms of itself at another point, and it was always defined, the input of a recurrence is always some arbitrary number, some unknown number n. Okay, we might have f of n equals f of n minus 1 plus 1. That would be an example of a recurrence. Okay? Where we are defining a function in terms of itself at another point. Okay, notice the input size is different than it is here. And in order to make those two equal, we have to add on values. Okay? So this is an example of a recurrence. An initial condition is similar, but instead of defining itself, or defining in terms of itself, we give a specific input value. Okay? So when the input size is 0, the number of basic operations we run is 4. Okay, this is just an example of an initial condition. This gives us a basis to work from. Yes?
So you would say that an initial condition would be a recurrence with a predetermined number?
It's not really a recurrence. It's an initial condition gives us a specific number of times a basic operation runs at a specific input size. Okay? So gives us the number of basic operations that are run at a specific input size is what an initial condition is. Okay, it's a ground. All right, part B. Be able to identify the basic operation of a recursive function. I gave you a recursive function. So what is the basic operation here? Now remember, you want to go back and look at some of the examples before. The simple one that we covered in class dealt with recursively computing the factorial of a number. And we said the basic operation was multiplying. That's what we're doing over and over again. If the condition for the base case is simply checking to see if an input value hits a certain point, so keep doing it until the input size equals 0. Don't set that as your basic operation. Okay? Look at what the algorithm is doing. You're multiplying over and over again. That's what your basic operation is going to be. Right? Last part, be able to set up a recurrence and an initial condition for a recursive function. We did lots of this. Okay? We did lots of this. So go back and look at the video. Notice what is not listed here. What is not listed here? Explain, identify, set up. So, solve. Just say. Identify the basic operation. Explain what recurrences and initial conditions are. Set up a recurrence and initial condition. No solve. Okay. Good? All right, moving on to part 4. recursion. So, part A, know how to identify the base case. Again, this is really simple. Recursive functions will always have a base case and a recursive case. The base case is the part that stops the recursive calls. So in this situation, our base case is this if statement. If x is less than y, return x. And when you're doing this on the test, if you just circle the if statement or you just circle this, that's fine. I'm not picky about what it is. If you circle the whole thing, that if x is less than y, return x, that's also fine. Okay? All of that is part of the base case. Again, it's the part that stops the recursive calls. It stops the continuing down the rabbit hole. The other part is the recursive case. That is obviously the part that contains the recursive calls. Okay? Recursive functions have to have base cases. That's the stopping point. Otherwise, it would go on forever. Okay. Part B says, know how to follow recursive calls. So you're going to remember that homework assignment you guys had where you solved those 3 recursive problems? You need to know how to do that on your final. Okay? There's a video of us in class where we wrote a function like 4 times and we followed it step by step through the whole recursive function. You're going to do something like that on your final, so make sure you know how to do it. Yes?
So that's more like they give you input, you have to follow it through this.
Correct. Yeah, it's not solving a recurrence and doing, it's actually, here's a recursive function. I pass in the value of 7. What do I get at the very end? Okay, you're actually solving it, not in terms of some unknown number n, but an actual input size. Okay, this just assesses your ability to understand and follow recursive calls. Okay.
Just like homework.
Yep, exactly like the homework. So again, this is a sample. What will be returned as a result of the call request 4.3? The answer is 6. This is an example of what you'll see. Something like this. Questions? All right, number 5. Be able to explain how a binary search tree determines where new objects are added. All right, I'm not looking for anything groundbreaking here. I'm looking for your understanding of the logic for how binary search trees are structured in terms of where objects go in relation to objects that already exist in the tree. Okay, specifically, understanding that objects whose value is less than or equal to go down the left side, objects that are greater than go right. Okay, that's it. Questions on that? Hash tables. 6. Almost over. Be able to explain how the size of the array affects the likelihood of collision. Something we talked about a lot, hopefully is kind of fresh in your mind. The larger the array, the more available spots there are, the less our compression method has to take the key and squeeze it into a smaller space. Therefore, the less likely we are to encounter collision. The larger the array, the less likely we are to collide. Question? Part B. Create a hash table from a set of numbers. This is something we did in class twice with 2 different examples. Okay? Question?
This is small. To get the key is mod size minus 1?
No. Are you talking about the division method?
Mm-hmm.
The division method is key mod size. So the unique identifier, remainder division, size of the array. Okay? Don't do minus 1. Key mod size. All right? Good question. So, create a hash table from a set of numbers. An example to that, first of all, if you go to the topic outline for hash table and scroll all the way down to the bottom, you'll see the 2 examples that we did in class. It was the one that says, create a hash table out of the following set of numbers using the division method, and I will give you the method for handling collision. It'll either be open addressing or linked chaining. Okay, I will tell you how big the hash table is, and I will provide the keys for you so you have everything that you need. It'll be just like we did in class. Okay, again, just assessing your knowledge of hash tables and the whole process. Okay. And part C is related to part B. You need to know the 2 different methods for handling collision. Linking or chaining is where each element of your hash table is also a linked list. You chain them together. And open addressing simply goes to find the next one in the next open spot. Okay. Yes?
Would we just be answering like a fill in the blank answer for that, or would we be showing the difference?
You'll need to be able to work out a problem that uses that. All right, last two. So first is tree traversals. We did a good bit of tree traversals in class, and you also did them on your third programming assignment. So again, nothing groundbreaking here. You need to know pre-order, post-order, and in order, and you need to be able to run them on a sample tree. So I'm going to give you a tree like this, and I say, tell me the order that the nodes are visited if we used pre-order traversal. Okay, so if this is your tree and we ran pre-order traversal, the answer would be 84793 You can practice using this example. Should be relatively self-explanatory. Finally, for heaps, I'm going to tell you one of your free response questions on heaps. You need to be able to tell me where new elements get added. So if we're going to add something to the heap, remember, it always goes to the next open position, top to bottom, left to right. So find the next open position, that's where it goes. And you need to be able to create a heap out of a set of values. So if I say, take these 10 values, 8, 14, 7, 100, whatever, take all of them and add them to a heap, or create a heap out of them, you need to be able to do that. There's an example in the heap topic outline of that happening. Okay, and we did that in class. Draw it each step, show the swaps, we'll add the objects one at a time. Okay? And that's it. That's your fun. Questions? Was that the first one? Know where new elements are added. So remember, heaps can't have holes in them. And so when you go to add a new element, there's only one place that it can go. And that's the next open position along the bottom row. If the bottom row is completely filled out, you go down to the next row all the way down at the left side. Okay? So you can always know, because there's only one correct place to add the next element. So that's how you always know where new objects fit out. Okay. All right, again, that's should be pretty clear if you go back and look at the topic outline. Questions from me?